One of the difficulties, particularly in stroke PCR, is the reliable measurement of an intentive command, of intention. When starts the intention? What is it? At which direction goes the intention? What do I want in the future? If I could decode a clear intention from the brain, then I could transfer this intention to an intelligent prosthetic device, and the prosthetic device does this. So if I have a glass in my hand and my intention is drinking, then I give the intention from the brain to the intelligent peripheral computer, who then moves my hand exactly so that I can drink the glass. Now, in humans, we still have the problem that the recording, artifact-free recording of intention, growing intentions, is very difficult. Intentions are represented in the brain in multiple, what we call slow waves, slow changing waves of the EEG. And humans usually have not just one intention at the same time, but they have many overlapping intentions. Of course, if you are a very hungry person and you haven't eaten for 3 days, then everything is concentrating on the food. And then we will have a very clear slow wave here, and we know this wave will give her the intention. But I don't need a wave for somebody who's hungry for 3 days to find out what intention he has. So the problem is really we have now is that we have these many overlapping intentions from different brain areas at the same time, and we have to find out what's the most important one. And we have to find out in seconds. So we don't have much time, because when I think, oh, I want to get up, then at the same time, my brain says from another part, says, well, but you haven't finished this. Another slow wave starts. Then I look out of the, while I'm standing up, I look out of the window and say, oh my God, there's snow outside, I have to change my tires, and so forth and so forth. So we have many overlapping intentions, which starting at totally different rise times. And since we don't know in these people what the aims of their intentions are, we make a lot of errors. So what we do now, when we have such an intention in the brain, we then, of course, activate the system, and the patient starts the movement, and then the computer asks, is it right? Is it right? And when the brain produces an error response, which we know there are error waves in the brain, then the computer stops it. But it's very cumbersome, and of course, even the response of the error is full of errors. So the identification of specific intention is so far a very difficult thing, but I have no doubt that we can solve the problem, because it's a sorting problem. Which is the most important intentions? Where it originates in the brain, which one we are using now, and probably with a learning system, a system can learn after several errors what type of intentions and what kind of brain waves is the correct intentional wave. But so far it doesn't work very well. In stroke, but also in communication, we have an average rate of correct responses of 70%, which means in 70% the response which is intended is executed, and in 30% there are errors. So there are a lot of errors. It's frustrating. But in the communication with the paralyzed, we reduce it now with this question-answer system. It's like an automatic lie detector. So you ask, what is the main city? The main city of Germany is Paris. Then the brain says automatically no. You grab the no, and then you ask the question, and you ask the contrary question. You say, the main city of Germany is Berlin. Then you look at the yes response if it comes. And then you can again ask a control question, and you say again, okay, the main city of the main city of Germany is Paris, and then you get an additional error response. And then the computer says, you're right, the main city of Germany is Berlin. And then the patient can say yes. So with this kind of strategy, you can reduce the error rate to about 80%, 20%.